Hi, welcome to chapter 3, getting everything set up. How are you guys doing today? I'm excited. This is chapter 3. Chapter 3, part 1. Glad you guys are all here. It's good to see everyone today. So as usual, we're going to start. I have lots of questions prepared. I secretly hope we get through all of them, but I'm no promises. Oh, good. Let's see. Other things I have for you guys today. It's September, which is exciting. I am going to get pumpkins to put by my door, like to decorate for fall, which will not be here for like 8 more weeks, but we can pretend, right? We can just pretend a little. So as you guys show up, it's good. Let's see what other excitement I have. I made chocolate chip cookies the other day. They were pretty good. They've lasted a lot longer than usual. I'm not really sure what that says about me, but I've been enjoying it. So before we really get started today, we're going to make sure that works. If you have any questions, drop it in the chat box. If you have no questions, that's great. You can always stop in and say hi. So let me make sure that's not going to make any noise. Make sure the rest of my devices will not make noise. Okay, so a couple of things. Most of you seem to be staying on top of your weekly assignments. It opens on Wednesday at 5. There is one today. It's due on Sunday night. On Friday, the rest of chapter 3 will come out. So exam 1, that information is going to come out on Friday, and it's going to cover chapters 1, 2, and 3, all of 3. So I split chapter 3 in 2 parts because it's probably the more advanced material that we're going to talk about. So covering it over 2 weeks is going to be great. Your ALEX objectives for chapter 3, part 1, also due Sunday night. Pretty much your due dates in this course are Sunday nights. That way it's easy. You can always remember it. We will always do live. I think there might be some confusion about when and where my office hours are. So my office hours are usually mostly on Zoom. So to get to Zoom, here's what you do. On the home page in Canvas, so at the top there's like a picture and there's a bunch of information. It says office hours, and then there's like a bracketed blue hyperlink called Zoom. Just click that during office hours and that'll take you right to where I am. Those are probably going to move. I will communicate any changes like I did this week in Canvas so that you have it. Do you guys have any other questions before we start on chapter 3, question number 1. So Mariah asks, we only have 3.1 ALEX and the weekly assignment. Correct. Those are the only 2 things that you have due this week. And they are both due on Sunday night. Great question. Also, while you guys are getting your lives together to take notes, you probably need a periodic table. I'm a little winded because I left this on my desk and I had to go run and go get it and then come back. So we're going to use a periodic table. I will provide you a link to a periodic table in the exam, or there will be one embedded. So there will be one. But the easiest way to do your homework is to use this. Now, you could have a periodic table in the front cover of your textbook. You can print them out off the internet. They're pretty much all the same. I would print the one that I posted, which is this one. It's obviously in green fun paper, mostly because it's the one that I will be using today, but that's all. If you ever have questions, drop them in the comment box, but let's look at number 1. So we are still true life. I'm writing the struggle bus because right here these should be subscripted, but I spent 30 minutes trying to figure it out today. I am going to put in I'm using this cool software in order to do this, to input the text up here. So I'm going to email them and figure out how to get these to be subscript. Or for the rest of the semester, they will just be big, and we will all know that they should be subscripted. So stay tuned. Okay. So for our first question, we're going to balance a chemical equation. So in this case, the combustion of propane. So propane is C3H8. And so when we think about a combustion reaction, combustions are pretty simple. It's whatever you're blowing up plus oxygen. Okay, that's a good sign. So oxygen is a diatomic. So there are 7-ish diatomics, or it makes a 7 on the periodic table. Nitrogen, oxygen, fluorine, and all of the rest of the halogens. So in that case, all of those, ooh, Bradley, that's a good suggestion. I might try that. Make them a different size font. Clever. So we're going to, it always makes the same thing. So the products for a combustion reaction are H2O plus CO2. Yes, and we're all still in frame. So what we're going to do now is we're going to balance this equation. So when we think about balancing this equation, now, for a combustion reaction, we can't use some of the tricks that I'm going to show you on the next example. But for this one, we can write out carbon, hydrogen, and oxygen. And over here, we'll write out carbon, hydrogen, and oxygen. So the first thing we want to do is write down what we have. So over here, we have 3 carbons, 8 hydrogens, and 2 oxygens. So, pro tip, these should make a line. They should be the same. Because otherwise, you can balance, like if this was over here, somehow you'd switch these two, you would balance the wrong things. So as long as they're even across, I have also seen students make tables where you basically draw lines. Any of those are fine. It works both ways. So from here, on this side, we have 1 carbon, 2 hydrogens, and 3 oxygens. So now we need to balance something. Now, one thing students always struggle with is what do we start with? So anything that's by itself, leave alone. So we want to leave the oxygen alone because hopefully we can just add a stoichiometric coefficient in the end and move on. So first thing I'm going to do is I'm going to try to balance the carbons. You could either start with carbon or hydrogen. Both of those will be a good way to start. So for carbon, I'm going to add a 3 here. So that gives me 3. So now I have 6 oxygens, but we're going to also alter the water. So we have an 8 here, so we're going to add a 4 here, so that gives us 8. And then now we're going to add 4 oxygens, which gives us a total of 10. And so that means that 5 goes here. So this equation does not have states in this case. So we will rewrite it. C3H8 plus 5O2 goes to 4H2O plus 3CO2. So on an exam or a weekly assignment, you should rewrite the equation with the stoichiometric coefficients in there. So some of you guys will start to see comments from Sarah. Sarah is our remote instructor. You will also occasionally see comments from Megan, who's our SI. Both of them will be answering questions. So, perfect. Okay, so the next example will be right on my face. So in this case, we're going to look at iron 3 hydroxide plus sulfuric acid goes to iron 3 sulfate plus water. So these are the types of equations where I think people start to get a little overwhelmed. There's a lot more things, and every single component has an oxygen in it. that just makes it even more difficult to look at and be like, yes, I know what to do. So this is how I like to think about it. So in this case, I'm going to rewrite the equation. Fe2SO4, and this has a 3 on it, plus H2O, liquid. Okay, so don't forget, well, that's not very helpful now, is it? There we go. So in this case, we want to go ahead and make sure we're writing down the states when we have them. But in chapter 4, we will memorize how to make states, but we haven't learned that yet. So one thing we do know is that most things can only break down into 2 components. So the iron and the hydroxide are 2 components. So instead of writing out a list of every element and then trying to keep track of them, because that's what gets hard, we're going to instead write Fe, OH, H, and SO4, 2 minus. So the sulfate ion stays together, and these 2 hydrogens will come off. So, and it's okay if you're like, I don't really know how you got there. That's okay. We're going to get there together a little bit more in chapter 4, but in this case, we know that the iron and the OH definitely break apart. And if this had been something else, we would see that as well. So on the first side, we have 1, 3, 2, 1. On the second side, we have 3 sulfates, 2 irons, 1 OH and 1 H. And so in this case, what we see is all of this. So what do we do first? Now, personally, just pick one thing to start with and then keep going. I'm going to start with the iron. So I'm going to start with anything that seems easy to rebalance. So I'm going to start with the iron, and I'm going to start with the sulfate. So iron first. We're going to add a 2 here to where that gives us 2 irons. Now we have 6 OHs. And then the sulfates. I'm going to need 3 of those. So then now we're going to have 6 hydrogens and 3 sulfates. So everything but the H and the OH is balanced. Okay? What do we do with that? Well, we can put a 6 right here, and that will give us 6 of each of these, and now everything is balanced. So we'll end up with 2 FeOH solid plus 3 H2SO4 aqueous goes to Fe2SO4 aqueous plus 6 H2O liquid. So when we think about balancing equations, a lot of times students get nervous because they're just like, I don't really know what to do. So keep in mind that all of these break down the middle. So what do I mean by break? Each compound is composed of an anion and a cation. So you should be able to see that. And so each one sets up. So Catherine asks, where do you see the OH on the right side? Great question. So the OH is part of the H2O, which is OH plus H. And so, yes, so Jeremy rewrote his as, y'all, I'm having a hard time today. I'm trying to make it to where you can see it because I wrote it kind of janky. So over here, what you'll see is that H2O could have also been written HOH, and that would have worked. You can set it up over here as these hydrogens and the oxygen. The reason I did something a little different on this case is because the oxygens and the sulfate make it a little bit harder to balance. But it looks like you are all caught up. Good. Good. Looks like you guys are all hanging in there. Okay. let's look at the next one. Don't forget, if you want, and I'd strongly advocate for it, there are handouts that you could download. This one, obviously, I wrote all over as a key, but you can try these on your own. So these are another place where you could do worksheets if you want more practice before the exam. So let's look at our next one. And I will try to write bigger. So in this case, now the other thing that you'll notice is I'm trying to name all of these components as I say them, because naming is important. We learned it in chapter 2. So as we move forward, we want to make sure that we know who sodium nitrate is. So first up, we have aluminum nitrate. Plus sodium Na2 sulfide. Now this one does not have states, so you are not responsible for making those up. So in the next, it produces aluminum sulfide and sodium sulfate. Now, in this one, it's a little easier to see that all of these break apart into 2 components. So our first one is going to break apart into the aluminum. There's one of those. We have the nitrate, and there's 3 of those. Now we have 2 sodiums and 1 sulfur. On the other side, there are 2 aluminums, 1 nitrate, 1 sodium, and 3 sulfurs. So the trick with some of these, and it's not really a trick, the best thing to do is to just start with any one thing at a time. If you try to balance everything at once, it gets complicated. So my suggestion would be to try to get this fully balanced, the aluminum and the sulfur. So I'm going to start with the aluminum, really just because it's on the top. So in order to do that, I'm going to put a 2 here. So now I have 2 of these, but 6 nitrates. So aluminum, balanced. Nitrate's not balanced yet, but neither is the rest of this. So our goal is to balance one whole side and then go back to the other side. So sodiums, there's 1 here and 2 here. So we know we're going to need to add something else over here. But we're going to need to add at least a 6 because there are 6 nitrates. So let's look at this sulfur. So we need 3 of those. So we're going to drop a 3 in here, which will give us 6 sodiums and 3 sulfurs. So now over here, we're balanced in 2 of our 4 components. So now I'm going to add a 6 here, which will finish balancing this equation. So the way I like to think about balancing, and you could have started on the left. I tend to start on the products because that's usually what controls things, not always, is I picked one element or one component at a time. And I picked things that looked unbalanced, but were easy to balance. Sometimes you will have to balance things twice, meaning you will get all the way through and have to go back and rebalance something else, multiply everything by some other component. It's important to note, when you balance an equation, they should be the lowest whole number ratios. So you could balance this by putting it a 12, a 2, a 6, and a 4, which no one can see because my question is right there. You could do that. But since we could divide through by 2, that is not the lowest whole number ratio. So make sure that they are, in fact, the lowest whole number ratios. So balancing equations can be quite frightening for a lot of students. But I think the trick of breaking it down into larger components, the anion and the cation, because at least in Gen Chem 1, things are only really going to move around in this manner. Or in a decomposition or a combination reaction, those I would suggest doing the elements alone. But those only have like 2 things and 1 thing. So Good. Next, we'll look at number 2. So we're going to start calculating the atomic weight. Because where chapter 3 ends is in limiting reactants. And limiting reactants is the ability to determine how much product you should get. So this week we're going to build the foundation so that next week, when I see you guys on Wednesday, we're going to know how to use the atomic weight, the mass percent, and all kinds of other cool stuff. So the atomic weight. Atomic weight is pretty simple. So for strontium carbonate, let me write that bigger. So strontium carbonate, what we need to do is we're just going to total up all the atomic masses, which is why you need a periodic table. So periodic table, then we're going to look in each box for the elements. So for strontium, it's 87.62. Carbon is 12.01. And oxygen is 3 times 16.00. Then we're going to add all these up in our calculator and get 147.68 grams per mole. Now, the periodic table, if you've downloaded this one, hold up. So, showing you my binder clip. Hold on. So strontium is right here, and it says 87.62. Good. But calcium has a third decimal point. We are only ever going to use 2 decimal points. So we will use traditional rounding in order to convert anything on the periodic table to just 2 decimal points. So, brief side note. Sig figs. On these, you just need to have 2 decimal places in your answer. So you can add them up separately, you could add them up before, but when we calculate the atomic weight, the numbers in our periodic table control that. So don't forget, in addition, it's about the number of places after the decimal. So the least number of those is how we do that. So our next component is silicon titanium dioxide. So now we're going to just add what we find in our, whoops, that's not a periodic table, but we're going to look in our periodic table for these. So we have 1 silicon, 1 titanium, and 2 oxygens. So oxygen is 16.00, titanium is 47.87, and silicon is 28.09. And so when we add those up, we get 107.93 grams per mole. So a couple of things. If you are watching this later, if you're not attending the live, or even if you're rewatching this to study, I would strongly advocate for you pausing, like when the problem pops up, trying it, and then watching this. Because I think one of the things I hope that you're all doing is doing lots of different things. Hold on, we're getting some comments that the answer to A was 147.63. Let me check. Plus 12.01 plus 16. Yikes. I am off by 0.05, so I must have just had a math error. So, note, A is 147.63 grams per mole. Malcolm, math, error. I'm so sorry. So this is for part A, which I'll leave up, or maybe I'll write it over here. So A equals 147.63, B equals, yes, working, 107.93. So let's look at C, and here's hoping that I didn't do another math error. So in this case, we're going to look at calcium phosphate. So when we think about all of these, they're all quite similar. We just look at the elements, look at the periodic table, and total them all up. So for calcium phosphate, the thing is, we haven't really encountered anything with subscripts yet. So calcium, there are 3 calciums, there are 2 phosphoruses, and 8 oxygens. So when we think about these, the reason there are 8 is because there are 4 inside the parentheses, and we have 2 copies of that. And so we need to make sure we're accounting for all of the different components in our molecular weights. So when we look at our periodic table, we get 3 times 40.08, 2 times 30.97, and 8 times 16.00. Hopefully when you plug this into your calculator, you should get 310.18 grams per mole. So other questions or thoughts before we move on to So I'm going to take a hot second to apologize because I'm uncertain as to how I got all of my numbers incorrect. So I'm going to start replugging them in before we do things. Let me check this next one. Okay. So it looks like on these 2, I made some small math errors. On the exam, I will take these kinds of questions and I will be able to use those. And so in that case, it will work quite fine. So don't panic about that. So other questions you guys are having today. I don't think so. So next, we're going to start using Avogadro's number. So our question asks, how many moles are in 15.35 grams of nitric oxide? So we're going to convert grams to moles. We're going to do this like a lot. So many times. But it's a good use of our time. So in order to do this, we need to determine the molecular weight. So the molecular weight is going to be equal to 14.01 plus 16.00, which gives you 30.01 grams per mole. From here, we want to convert grams to moles. So we're going to take our 15.35 grams of nitrogen oxide, and we want to convert that to mole. So we're going to use the molecular weight, which is right up here, to convert, the same way we would use density or any other unit conversion factor. So we have our 15.35 divided by 30.01 grams in 1 mole of nitrogen oxide. And when I plugged this in yesterday, I get 0.5115 moles of NO. And I am going to double check that because apparently math today and I are not friends. I get the same answer today. So in this case, what we see is we're going to take the mass that we have and use the molecular weight as a unit conversion, grams on the bottom, moles on the top. I would also recommend that you write out your units. Get in the habit now, because as we move forward, the ability to convert, to now know that this is moles of nitrogen oxide is going to be helpful. So our next question is calculate the mass of iron 3 oxide, Fe2O3, that contains 2.95 times 10 to the 9th oxygen atoms. So this one is a little bit more complicated. We're going to use Avogadro's number because we want to know what mass contains the number of atoms. So we can use Avogadro's number to get there. So first we need our molecular weight, which is 2 times 55.85 plus 3 times 16.00, which gives us 159.70 grams per mole. So we have a molecular weight, which is good. Now we got to figure out what happens next. So we're going to take the number of atoms, and we have 2.905 times 10 to the 9th oxygen atoms. So we want to convert that to grams. Avogadro's number will get us to moles, okay? So we are going to say that there are 6.022. First, we're going to say that there are 3 O atoms and 1 Fe2O3. Now, this isn't 30, it's just 3. So in this case, that's hard to see. There's 1 oxygen atom. Oh. Thank you. And there are 6.022 times 10 to the 23rd Fe2O3. We're going to run out of space. And 1 mole. Because of the board work, I'm going to do at the bottom. There's 1 mole of Fe2O3 equals 159.70 grams. And I for sure did this calculation wrong. It's 2.095 times 10 to the 9th divided by 3 divided by 6.022 times 10 to the 23rd. Multiplied by 159.7, and so the final answer is 1.852 times 10 to the negative 13 grams of Fe2O3. So this is a pretty long calculation, and you can't actually see it. So keep in mind that this part just starts right here. I will experiment with a new camera location. Maybe if I push it a little bit further back, you guys can get more board workspace. Or, yeah. That line just tells me how far over I can go, and that will solve this problem. So in this case, it's just a methodical calculation. So Ms. J asks, let's go through it again. So, and the more of these examples we do, the easier it will get. So this is what we started with. This right here allows us to convert from oxygen atoms to molecules of iron oxide. So when we look at iron oxide, which is Fe2O3, in this molecule, we now have, we're going to make this go away, 2 Fe's and 3 oxygen. And so what I did here was I converted from oxygen atoms to molecules of Fe2O3. So from here, this is molecules. From the molecules, I converted into moles of Fe2O3. Because for every 6.022 times 10 to the 23rd Fe2O3s, that's 1 mole. And then I used our molecular weight of 159.7 grams in 1 mole to give us our final answer. So as we think about all of these, and there's lots of examples, I think we have 2 more kind of similar to this, that will help us start to think about how this works. So, let's see, other questions. We'll work the next example, and hopefully that will start to kind of help. I've also tried to pull some questions that are quite similar to your ALEX objectives. So this one came from an ALEX-like objective. So this one asks, how many copper atoms are in a 100% copper penny that weighs 3 grams? So in this one, we don't need to calculate the molecular weight, but we're going to convert a 3-gram copper penny into copper atoms. So we're going to take our 3.00 grams of copper. This came from the problem. Now we're going to convert using the molecular weight of copper from the periodic table, which is 63.55 grams of copper and 1 mole of copper. And 1 mole of copper contains 6.022 times 10 to the 23rd copper atoms. And so that's the entirety of this calculation, because it just asked how many copper atoms are in a 100% copper penny, and it weighs 3 grams. So when we plug this into our calculator, we got 2.84 times 10 to the 22nd copper atoms. So if you are using a scientific calculator, please make sure that you know how to do this type of a calculation using the times 10 to the 23rd. If you're using a graphing calculator, you also need to know how to do this calculation. So please make sure that you're getting these answers. Now, you might be asking, why are the sig figs only 3? This has 4, this has 4, but this answer, this number which came in the problem, so the data in the problem, in this case the 3 grams over here, is what controls the number of significant figures in this case. So let's do another example. So this asks, how many glucose molecules are in 5.23 grams of glucose, and how many oxygen atoms are in this sample? So this is going to be quite similar to the first one of these that we did. We're going to calculate the molecular weight. Make sure you guys can see that, which is 180.18 grams per mole. So we're going to take our 5.23 grams of C6H12O6. We're going to multiply that by the molar mass, which is 180.18 grams in 1 mole of C6H12O6, and 1 mole of C6H12O6. There are 6.022 times 10 to the 23rd C6H12O6. So once we plug this into our calculator, which would be 5.23 divided by 180.18 multiplied by Avogadro's number, that will give us 1.75 times 10 to the 22nd C6H12O6 molecules. From here, so that's the first question, it also asks how many oxygen atoms are in this sample. So there are 6 oxygens in each 1 glucose. So in every 1 C6H12O6, there are 6 oxygen atoms. And we get 1.05 times 10 to the 23rd oxygen atoms. Whoops, can't quite see. So far today we've talked about balancing equations, which is fun, calculating the molar mass, and using Avogadro's number or converting grams to moles. So the next 5 examples are just other types of calculations that we're going to look at today. Empirical formula, the mass percent, in all of these cases. Again, if you have a question, feel free to drop a comment in the comment box. So far, it looks like you guys are following along, and hopefully there are less math errors. So in silver oxide, which is Ag2O, we'd like to know what percent by mass is silver in comparison to the total mass. So in this case, when we think about these type of problems, the first thing is the molecular weight, which we calculate the same way. So in the interest of time, I will go ahead and just give you that value, which is 231.74 grams per mole. So this is the total mass. So percent mass is whatever component it is divided by the total mass. So we're going to take 2 times the mass of silver, which is 107.87. Divide that by 231.74. Multiply that by 100, and so we'll get 93.10%. So I gave this value. You could also give me it would be equally correct to say 93.096%. So star sig figs. So typically, significant figures are not determined by the mass. In these calculations, you can either have 2 decimal points to round to the number of decimal points that you usually use in a periodic table, or you can use the mass values to calculate the number of significant figures. I will accept both in both cases. So Cassidy asked, what is the mass percent formula one more time? Sure. I'll put it over here. So mass percent is the mass, I'm sure this can be seen, that cannot be seen. So it's the mass of element divided by total mass. So in this case, it's 2 multiplied by the atomic mass of silver. So you could have also written it like a shorthand of 2Au over Au2O. So it's the mass of whatever element of interest divided by the total mass. Good question. So we have another one of those. Move it down a little bit. So in this case, we want to know what is the mass percent of lead in lead 2 nitrate. So now the first step actually has to be to determine the chemical formula of lead 2 nitrate so that we can calculate the mass. So we know that lead is Pb. The Roman numeral 2 in this word tells us that it's a 2+ charge. Nitrate is NO3-. And so that means that we're going to need 2 nitrates in order to balance the charge for the lead. So our chemical formula is going to be lead PbNO3 2, which tells us that we have 2 nitrates for every 1 lead. So next we're going to calculate the molecular weight. Is going to be lead plus 2 nitrogens plus 6 oxygens is going to give us a mass of 331.22. So we are going to use this total mass in order to calculate the percent of mass by the lead percent. So we're going to take the mass of the element. So in this case, we only have a single lead atom per total. So it would be 207.2 divided by 331.22 multiplied by 100. And that's going to give us a mass percent of 62.56% lead. So mass percent is just the ability to determine what percent by mass in a whole mole. So we could do it in a fractional component. We could do lots of different types of things. But we can always use the mass percent where we determine the mass of the element divided by the mass of the total mass of the compound. Do you guys have any questions? How are we feeling about this? Am I making a whole lot more math errors? I am going to start erasing this so we can do the next equation, the next question. Oh, good. I think this stuff is super easy too. So this next question tells us this is a different ALEKS objective. So our chemist determines that 0.2836 moles of osmium was utilized in the reaction. What mass in grams of osmium was used? Pretty simple. Now you might be like, is osmium a compound or an element? It's an element. Osmium is OS, it's element 76. So we're going to convert grams to moles, or moles to grams, sorry. We're going to take our 0.2836 moles of osmium. Now, osmium is element 76. You can find it on the periodic table. So we want to convert to grams. Now, we need to find the molar weight or the atomic mass or the atomic weight, whichever version of that, or the formula weight, whatever one you like. In this case, it's just directly from the periodic table. So in 1 mole of osmium, there is 190.23 grams. So when we plug this into our calculator, we get 53.95 grams of osmium as our final answer, with like a decimal point that y'all could see. So in this case, this is just a different molar mass conversion example. Now, what we will do is in the rest of chapter 3, so next week, we're going to do more calculations like this, or we'll go from grams to moles. So we want to be really familiar with this. So our last two examples today, which we have just enough time for, we're going to start to look to say, can we figure out the composition of this compound using information like the percent composition? So, these are having some hard, nope. Hold on, struggle is real. Okay, so our compound has a composition of 62.6% carbon, 4.2% hydrogen, and 33.4% oxygen. What is the empirical formula? So, in the video, I talked about how it has three steps. 1, assume 100 grams. Step 1. So we're going to start with that. So you might be like, 3 steps? I don't remember that. That's okay. We're going to go over it. So in this case, we want to assume that you have a 100 gram sample. Now, why 100 grams? It makes the math easy. You could assume that you had any other weight sample, but you would have to convert it. I choose 100 because if we choose 100 grams, so for carbon, when it is 62.6% of 100 grams, that is 62.6 grams of carbon. For hydrogen, which is next, it's 4.20 grams of hydrogen, and oxygen is 3.34 grams of oxygen. These three numbers add up to 100. So the 100 gram assumption allows you, very simply, to make easy math in order to find these values. You could do 5 grams, 10 grams, 100 grams, 1,000 grams. After this, the math is the same. So from here, so step 1, assume 100 grams. Check. Next step, 2, convert to moles. Okay, so to convert to moles, that's kind of the same thing we've been looking at. We're going to divide by the atomic mass. So for carbon, it's 12.01 grams in 1 mole. And that gives us 5.21 moles of carbon. For hydrogen, we're going to divide by 1.01 grams in 1 mole of hydrogen. So that gives us 4.16 moles of hydrogen. For oxygen, we're going to divide by 16 grams in 1 mole. And that gives us, 2.09. Now, some of you will be tempted to forget about step 3 and just say, oh, well, there's 5 carbons, 4 hydrogens, and 2 oxygens. So that doesn't work. So these are all still in a percent value. So we need to divide by the least moles. So from here, we're going to divide by the least number of moles. So the least amount of moles that we have is oxygen. We're going to divide by 2.09, and that's going to give us 1. Here, we're going to divide by 2.09, and that's going to give us 1.99, which is frankly pretty close to 2.0. Here, we're going to divide by 2.09, and that gives us 2.5. So like we did in the video online, that you can't see that. So online, we actually don't ever have half moles. So we're actually going to divide, so 2.5 is 5 halves. So we're going to multiply through by 2. And so we end up with carbon 5, hydrogen 4, oxygen 2. Which I'm going to be honest is very close to these numbers. However, that will not always work, and it almost never works out this way. So in this case, this is our plan. We're going to assume that you have 100 grams. Then we're going to convert to moles. Once you convert to moles, once we got here, we need to divide by the least moles. So in the example we do next, we will see that the least moles, none of those are near a value. Any questions before I erase this? Because I feel like someone might have some questions about how this worked. So I will just hang tight. If you have no questions while I'm kind of hanging out, you can go ahead and start this next one up here. And I will start that one just in a hot second or so. So when we think about these, I like to give phases. So I will switch sides so we can see the phases, or a task list. Because I think reading a question being like, I don't know where to start. So I will always try when I have a plan, because a plan of attack gives you at least somewhere to go. So in this case, our plan of attack is to assume that you have 100 grams, convert to moles, and then divide by the least moles. So Cassidy and Miss J would both like to know, why did we multiply by 2 at the end? It's a good question. So let me find a blue marker, which will hopefully show up, but maybe not. So when we got 2.5 here, so the answer could have been, so at the end, these equals values tell you what the subscript are in your compound. So we would have gotten carbon 2.5, hydrogen 2, and an oxygen. So the problem is that we can't have 2.5 oxygens. We can only have a whole number of oxygens in any compound. So what we need to do is to figure out how to get this into a whole number. So what we did is we realized that 2.5 is the same as 5 halves. So we have carbon times 5 halves, hydrogen 2, and oxygen, there's just one of those. So one way to get rid of that is impossible to see. I'm going to walk over there, wherever the board is, over there, and I'm going to write bigger so we can see. So if we have carbon 5 halves, hydrogen 2, and oxygen 1. In order to get rid of that, which, you know what, that didn't work at all, so we'll just go back to this and try again. So we need to get rid of this. 2.5 is 5 divided by 2 in fraction form. So we can just multiply through by 2. So when we multiply through 2 times 5 halves, gives us just the 5. When we multiply this through by 2, it's just because we have to do to all of them. So what we're trying to show, and I'm sorry, I may be overthinking the video, in which case, my bad. But this allows us to convert this back to a whole number. So most of the time, it will be fractions that you know. Halves, quarters, thirds, that's it. So if you were to have gotten 1.3, so 1.3 is the same as 4/3, so you would have multiplied through by 3. These are not super common, but they are relatively common in these examples. You'll see lots of them in ALEKS. So we multiply through by 2, it's a very long-winded answer, to get rid of the fraction part. Good question. Too much talking by me. So that's not going to help me. Let's do it just like that. So let's look at our next example. I will leave up our plan of attack so that we can use it, but I will rewrite what I forgot. So before I go on, Aquatic Misery asked, if carbon had been a whole number, would we still need to multiply by 2 because oxygen is a diatomic? So no. In this case, this is a compound and oxygen is not a diatomic. So in the molar mass, we don't need to multiply. It is only 16 grams per mole because it in this case is not the diatomic. We only treat oxygen as a diatomic when we see it in a chemical component. In this case, in these problems, as we'll see in the next one, we will not need that. So if the number for carbon had been any whole number, we would have used them directly as is. Good question, Aquatic Misery. So for our last question of the day, it says, what is the empirical formula for a compound that is 41% yttrium, another weird element we haven't met before, 36.9% bromine, and 22.1% oxygen? So, yttrium, you're like, I don't even know that, kid. Yttrium is Y, it's element 39. So we're going to start with step 1. We are going to assume that we have 100 grams. So for yttrium, we're going to take our 41.0 grams of yttrium. Then we're going to take our bromine, which is 36.9 grams of bromine, and our 22.1 grams of oxygen. So by deciding it's 100 grams, it just makes the math easy. You could do it with other ones and that would be fine too. So now we're going to convert from yttrium into moles. So we're in step 2. So the molar mass of yttrium is 88.91 grams in 1 mole of yttrium. And that gives us 0.461 moles of yttrium. When we convert bromine using the molar mass of 79.90 grams in 1 mole, that gives us 0.462 moles of bromine. Oxygen divided by the 16 grams in 1 mole gives us 1.38 moles of oxygen. Now, you'll notice that none of these numbers are anything close to a whole number. We have 2.46s and a 1.38. So we couldn't round these into whole numbers and kind of just cross our fingers and hope. So in this case, the third step makes a little bit more sense. So we're going to divide by the least moles. So the smallest number of moles is 0.461, which gives us 1.461. This gives us pretty much 1. When you plug that into your calculator, you'll get like 1.0001, rounds to 1. And 1.38 moles of oxygen divided by 0.461 gives us 2.99, which rounds to 3. So the empirical formula in this case will be to take each of these to give us our components. So our compound is yttrium, bromine, O3. So I'll let you guys, what questions do we have about this example, about any of the examples we've done earlier today, other things? This is the first half, really, of chapter 3. The only thing that is not in our examples today is the ability to use this if we also have the molar mass, but there are several examples in the video lectures in 3.4, I think. Yes. So, other questions today. Do you have any questions about what we've done? Questions about what's happening next this semester? What you got? I think the first half of chapter 3 is pretty easy. I'm excited that we're going to have a little bit more time to really kind of think about it in between as we move forward. The next parts of chapter 3, those videos will go up on Friday. And so there are 2 more videos coming, just 2. They are probably the harder material in chapter 3. So I'm excited that we'll have 2 full weeks to think about that. Aquatic Misery asked, how do you know what order to put the elements in? For my class and anything that I grade, I will accept them in any order. My recommendation would be to write them in the order they're given in the problem, because that's usually a safe bet. And so for yttrium, bromine, and oxygen, you could have written them in any order, but I wrote them in this order because I wanted to, pretty much. Oxygen is almost always last. I think Alex is picky about some compounds, but I'm never quite sure which ones they're super picky about and which ones they're not. So a safe bet is always to go with the order in the problem, which is usually what I do. Kajal is correct that the exam is on September 16th. So next week we will have a live session. The following week, during this time period, from 3 to 4:15, will be our exam. So it will be through Canvas. And so it'll be on Canvas. Like your weekly assignments, you'll take pictures of your work and upload those. Okay. We've got a lot of questions. This is exciting. So Nicole asks, where's the best place to get additional problems that are similar to the ones on the exam? So the options that I've provided, the weekly assignment is good practice. I have written all of those questions. They are on track. They are similar, but not totally similar to an exam. These components, I wrote most of these questions as well, and so those are kind of similar as well. I also provide a worksheet that is totally optional. Those are kind of similar. So those 3 items, there's also a list of problems in the back of the book. So those are what I would kind of think of as where to go forward. There will not be a practice exam posted on Canvas. The weekly assignments, I did try to write questions for this one and the next one. Really everything you've seen thus far are quite similar to what I would ask you on an exam. They will be worth more points. Okay. Then Miss Keisha, asked, having trouble accessing the textbook in Alex, where can it be found? So you have 2 choices. You can purchase the textbook through UNF. You can rent it online through any rental agency. You can buy it on Amazon. Or, and in my weekly announcement this week, I will post a link. There is an open access textbooks, which is basically like a web page textbook. And so that is free. It is mostly the same in that case. So you can go and look there. Catherine asked, on Alex, is the objective knowledge check a graded assignment? No. So Alex grades, it's a long game. So I will only look at your Alex scores at the end of the semester, at your final exam. So you will take a final and I will look at Alex. So you need to complete your PI by the end of the semester. The knowledge check converts the blue bar at the top from dark blue or from light blue to dark blue. It says that you learned something. So maybe you found that some of your objectives went away. Before we full on panic, which is an appropriate option, you will have access to those anytime you finish the weekly objectives early, anytime, or there will be a period of time right around exam 1, 2, Thanksgiving break, 3, and the final, where we'll have something called Open Pie. And during Open Pie, you can access anything in any order. So Kajal asked, can we only use a scientific calculator on the exam? A scientific calculator is recommended. It is the required materials for this course. It is online, and I prefer that you use one. We'll leave it at that. Ms. J would like to go back to number 1, part B. I like it. Why did you get OH and leave the other H? Do we have to do that every time when we have water? Yes. I like your comment. So it's because the product side is like that. So I prefer, this is how I taught myself how to balance equations, which is why I'm teaching you to do that. So I only want there to be only 4 things to balance, because it's easier than trying to juggle all of the different places where oxygen goes. So I split it apart into OH and H because I could see that they were both on the reactant side and on the product side. So you're totally right. Emily asks, do you have any tips for memorizing the common ion table? What I have seen students use in the past are index cards with like name and formula on different sides. So that's one option. I know that there is a Quizlet, which I'm not exactly sure how Quizlet works, but there are some common ion Quizlets that you can find online. And there is a way that you can go back and see objectives that you've already completed. It will not take away points, but you can go back and retry any of the ALEKS objectives that you've learned. Camilo asks, so all of the questions on our exam will be short response, pretty much. So I like being able to see your work. So this process here of me showing you guys how to set up all these calculations and how to do this, there will be very few answers where there are no multiple choice, I can tell you that. I do not like multiple choice. So in this case, let's say you had made a mistake. Here you had used some other mass. You would get entirely different answers. I will award partial credit based on your work. So you will answer things in Canvas, and then you will upload your work as well. And both of those together will get that. So Ms. J asked, for combustion, we will always have to include oxygen. Yes. So in a combustion reaction, it is always whatever is blowing up plus oxygen gas, which is O2, and that gives you CO2 and water. Always, 100% of the time in Gen Chem. In organic, in Gen Chem 2, you will combust other components, which will make other things, but we will only use those. So, oh, Ariana has a really great idea to using the chunking method, which I really enjoy that. One day she studies the +1s and the -1s, and then she'll do the -2s and the -3s. I like that plan. Kajal also mentions the Quizlets. Those are the things that I would kind of suggest. Carson asked, do we need to use a lockdown browser for the exam? That information will come out on Friday. I'm trying to make sure to give you only one set of information. So on Friday, I tend to post those like very long announcements. A big part of this one will be dedicated to the exam, in addition to everything else that's usually in there. So we will probably be using a lockdown browser. There will be a test, not a test. There will be a way for you to make sure that it works before we get to the exam. So that's helpful. Any other questions today? If you guys have questions, don't forget on Friday I have office hours in Zoom, which you can access from the homepage by clicking the Zoom link. And If you have any other questions, you can send me emails. I'm happy to help in any way I can. If you get stuck on your ALEKS and you're like, I just need some help, feel free to send me a screenshot of the question and your work, and I'll be happy to look at those. Any other questions? Any other thoughts today? All right. Well, I'm going to let you guys go. Y'all have a great rest of the day. Oh, wait. Jeremy says that there are some pretty prominent patterns. Totally true. So you guys have a fantastic rest of the day, and I will see you next week. And have a happy Labor Day.